display contours that represent pressure. So let's turn on a preview here. Okay, so you see we've cut through, sliced through the computational domain, and here's what the pressure contours look like. Now this is only, what, 10 different levels, so that kind of looks, I don't know, like, well, we can do better. Let's make it 100 levels for the pressure contours, so we get a much smoother looking plot, instead of something that's real segmented and chunky. Okay, so there's our contours, and you can see the air's coming in this way. We've got a region of high pressure on the front side of the sign, low pressure on the back side. You can even take this arrow in the preview and you can drag it, and you can actually see how the fluid flow changes as you get near the sign. Okay, and then see the effect of the sign, and then as you get back past the back side, you see the effect of the sign goes away. So we can also turn on the mesh in this cut plot by clicking that button, and now you can see, okay, here's the block size that it used to break up the computational domain, and it did do a little bit of refinement near the sign. You can see the blocks get a little bit smaller, which is good, but we don't know if that's small enough. There's going to be some very abrupt changes that happen in this region where this air first encounters the sign, and we would need to do some further study to decide if that grid size is actually adequate for capturing what's happening there. We can also turn on streamlines here. Okay. Now this computer has some graphics issues. When you do this on the lab computers, you will get a much nicer looking plot that looks like this one here. Okay, where you can actually see the streamlines are these lines that track where a particle of the fluid would travel. And what's really cool is you can see, okay, particles come in this way, they have to go around the sign, and then you get some recirculation on the back side of the sign, which is really cool to see that in your streamlines. You'll be able to see that in the lab, even though I can't show it on this laptop with this graphics card. But anyway, that's how you would make the cut plot, and that's one of the plots that I asked you to make for your homework. I should also mention, when you choose what your contours represent, in this case I did pressure, but you could also do temperature, velocity, any of these other things, it's a good idea to click this button to adjust the limits of your scale, because you don't know what they're going to come up with by default, but if you click that button and then click these two buttons, it will reset to the maximum value is the maximum pressure. The minimum value in your scale is the minimum pressure. So you're not truncating the results, you're not cutting off important information. So this is how you can set those limits. Okay, so that's the cut plot. The surface plot, I'll hide that one. Okay, surface plot, again, right click and say insert, and we'll just use all faces of the sign. So I just check that box, and again, we'll do contours, pressure, and 100 levels. We'll do the same auto range for the scale to make sure we don't truncate the results there, from the minimum to the maximum. And when we click the check mark here, what this does is show us the pressure distribution on the sign itself, as opposed to in the atmosphere surrounding the sign. So as you would expect, you get high pressure on the front side, low pressure on the back side of the sign. Nothing too surprising there. The last thing that's pretty cool, though, is the flow trajectories. I right-click and insert flow trajectories. Okay, this lets us pick a surface of the object that's going to seed particles into the flow. So I'll click the front surface of the sign, and you can choose how many particles get seeded into the flow. We'll just say 25. And you can choose what these are going to, or how these are going to be displayed. Pipes, lines, bands. You'll see the effect of that option in just a moment. And you can choose what these flow trajectories represent. Is it pressure, velocity? Let's do velocity on this one. And click OK. Okay, so this shows you how a particle of fluid would actually travel as it encounters the front side of the sign and then has to go around the sign. Okay, so the front side of the sign generated these particles, but SolidWorks tracked them backwards in time and forwards in time to show the motion of those particles. So that's pretty cool to see how the flow is going to go around the sign. But what's even cooler, if I go back and edit that plot, if I also choose the back side of the sign, that half and that half, and click OK. Now what you can see is you've actually got this region of air that's trapped in here behind the sign that never really gets blown away, but it just circulates with a fairly low velocity back here behind the sign. So that's the flow trajectories and the surface plot. So you'll turn in a plot that looks something like this. And this is all described on your homework handout. So you'll have the instructions for what you're actually doing in. And then the last thing I wanted to show you here is the surface parameters. Like say you wanted to know, okay, the wind is blowing at this sign, how much force is actually exerted over this entire surface of the sign? Well, you can determine that with surface parameters. If you right click and say Insert, choose the front surface of the sign, and choose what parameter you're interested in. Force is not listed by default, but just click More Parameters and you get all these other parameters that you can choose from. So I go to Loads and choose Force right here. Say OK. Then I've got Force selected in this list, and I can say Show. And SolidWorks will go through and calculate the total force exerted on the front face of the sign by that 50-mile-an-hour wind. Okay, the 22 meter per second was roughly 50 miles an hour. So it's 434 newtons, which is roughly, what, about 100 pounds? Something like that. And if you had a whole bunch of parameters you were interested in, there's a button that lets you just export all of this data right to Excel. So you can analyze it further in Excel. Okay, so that's it for our CFD analysis. Do you have any questions about the CFD side of things before we go to the FEA? Is this stuff interesting to you? Some of you? At least it's fun to see the cool pictures that we can make, right? If nothing else.
Could we do this with the Corvette?
You could. It would be pretty computationally intensive, but you could do it, yeah.
Does it accurately describe forces over wings?
Yes.
Cool.
It is accurate as long as the person using it sets it up accurate.
Right.
This doesn't really have to do with what we're looking at right now, but in like lecture, we were told that we were going to learn about the animation part of this for the oncoming assignment in lecture. Is that stuff that we've already learned, or stuff that we're yet to learn?
Well, what I showed you last week with the motion analysis was closely related to that. So all you need to do for that lecture homework is, if you go into the motion study tab like we did last week, and okay, let me go ahead and turn on what other add-ins. Let's do the SolidWorks motion add-in. Oh, it's not giving me these options because there's no assembly here, but so this by default is just going to do solid body animation, but all you do is like establish the keyframes down here on your timeline from 0 to 2 seconds. So maybe this is one keyframe, and then maybe you rotate into this orientation and establish a keyframe at 2 seconds, and zoom out, zoom in, establish a keyframe there, and just save it as an animation. So if you have questions about that, come up at the end of class and I'll be happy to show you in more detail about the animation. Okay, any other questions?
He also mentioned during lecture to ask you about diametric view.
Okay, so the different view types or view orientations, like you're used to using this button up here to get your front view, your top view, and stuff like that. Okay, well, in that same button, right over here is where you would get an isometric view, but if you click the drop down, this is where you can get a dimetric and a trimetric view. The difference between them, honestly, just has to do with how the different orthogonal directions are represented in 2D space. It's like, normally your X, Y, and Z directions are 90 degrees apart, right? Well, in a 2D representation, like an isometric, they're not 90 degrees apart. Like in this case, they'd be like, that may be like a 60-degree angle instead of a 90-degree angle on paper, if you measured it with a protractor. And if we went to a dimetric view, the angles are defined to be a little bit different, and a trimetric view, they're defined to be a little bit different. So that's all that that's about. But if you want to see those views, you can get them from the view orientation box right there. Okay, so what we would like to do, let me go ahead and hide some of this just to clean up the screen, hide the surface plot. In our FEA study, we're going to want to bring in the aerodynamic loads that we just calculated and use those to calculate what is the stress and what is the deformation of this object. So, and this is a selection that you just have to write down because it's hidden in the menus and you'll never remember it unless you write it down. But what you want to do to export our CFD results is go to the flow simulation menu, then go down to Tools, and then click Export Results to Simulation. So again, you're going to go to the Flow Simulation menu, Tools, and then click Export Results to Simulation. And it doesn't tell you that they've done it, but it did. And we'll find it when we need it. Okay, so now for the FEA study, we're going to go over to the simulation tab. And the way this one's a little bit easier to set up. So we can go to the Study Advisor button and just click the drop down and say New Study. And it'll say, what kind of study do you want to set up? A static study, that's what we're going to do. But you could also do frequency analysis if you need to find out, okay, any object has natural frequencies that it resonates at. What are those natural frequencies? You can do one of these frequency analyses. You can do a buckling analysis if you had a downward force on the sign and wanted to find out is the post strong enough not to buckle. You can do thermal analyses, a drop test if you want to find out if you slam your phone onto the ground, will it survive? That's what a drop test will tell you. Fatigue studies, linear dynamic, and a variety of other things. So we're going to do static for this type of study. Click OK. Okay, now if we have not defined the material for this part back in the original part file, we can do it here. So I'm going to right click on the part in study 1 and say apply or edit material. And let's make this one, let's do aluminum 2024. Say apply. Now what's nice is that all of these material properties are already built into SolidWorks for you. So you don't have to go to material handbooks and find out, okay, what's the modulus or the strength or the or Poisson's ratio and these other properties. You don't have to go look these up. They're already built in. But as a side note, if I go to woods and choose, say, pine, notice that the only number built in is density. Why does it not give me things like the modulus and the Poisson ratio and strength and things like that?
It's not constant.
Because it's not constant, exactly. Because you take two different pieces of wood, of pine, even though they're the same kind of wood, they could have very, very different properties. And SolidWorks doesn't want you to call them up or sue them because you used their properties and your piece of wood wasn't as strong as what they said it would be. Now with aluminum, there's standards that say if you're using 2024 aluminum, there's an ASTM standard that says it has to meet these requirements for these strengths and stuff, or else it's not certified as that type of aluminum. So if that happens, SolidWorks just points the finger at whoever sold you the aluminum and says it was their fault for selling something that was out of spec. Okay, well we've got aluminum set as our material now. If we push on the sign now, it's just going to go flying through space because there's nothing holding it down. So we'll go to Fixtures, right-click, and you can see a variety of fixture types that are defined for hinges, elastic supports, bearings, rollers, In this case, I'm just going to do fixed geometry and fix this bottom end of the sign, the bottom face, and say that that's constrained in all 6 degrees of freedom. Okay? Now, strictly speaking, is that accurate? Not really. I mean, it's probably buried in concrete, but at that point, it can still deflect. It can still, the point can still rotate a little bit as the post deforms. So, again, specifying the loads and constraints properly is perhaps one of the greatest pitfalls of FEA in getting good, accurate results. Okay, so if we go to loads, and we could simply apply a force or a torque or a pressure directly to the sign, but as I mentioned a moment ago, we want to bring in those aerodynamic loads. So you want to write this down, but what you do is right-click on Study 1, go to Properties, then go to the Flow Thermal Effects tab, go to the fluid pressure option and turn that on. I'll do this again in just a moment so you can see it again. And then you browse and find the file that contains your flow simulation results. Now, it will usually take you by default to the correct location where those results were saved, but the file you're looking for is just going to be a number.fld. So you select that file and say open. Okay, so let me show you that one more time. To bring in your CFD loads, you would right-click on Study 1, go to Properties, go to the Flow and Thermal Effects, check this box for fluid pressure options, and then browse and find that number.fld file. When you open it, you can make sure the file name matches what you're working with and say OK. Okay, so we've got material, constraints, loads. We're ready to go ahead and run this study. So it will generate a mesh. It will fairly quickly generate results. Okay, so it does these 3 plots, result plots for us. So on any of them, you can right-click and do Edit Definition. If you see, this is a stress plot showing von Mises stress. There's other stress components you can do. You'll learn all about these in Strength of Materials if you haven't taken that yet, to learn about the different kinds of stress. You can plot simply the displacement. So like here, this is exaggerated. This is deforms 16 times the actual deformation, but you can see how it's bending back, and the corners up here are folding back, so they have the greatest amount of deflection. You can look at strain, which again you'll learn more about in Strength of Materials. This strain is often the most important property for determining when something is actually going to fail. And if we want, we can right-click on the mesh and show the mesh that was used. Show mesh. So you can see how this part was now discretized into all these triangular little elements to determine what the stress and the motion deflection of this object were going to be.
Sir,
Yes?
is there any reason why it would be 16 times what the actual force would be, the actual deformation would be? Okay,
it just shows that, it just picks a number by default to exaggerate and show you how it's deforming, but you can turn that off. If you edit definition, right up here, instead of doing their automatic default scale, you can do true scale or any scale that you want. You can scale it just by a factor of 1, which would be true deformation, and you see it's not really deformed that much. Yeah, good question. Okay, any other questions? So back on the hand, I'll turn this on E2L as you guys are walking over to your labs, but I tried to walk you through it. You're going to download the road sign part. You're going to run a CFD study on it. I gave you the velocity for air to use. Just use fully turbulent like I did. Use the ground symmetry plane. And then you're going to run the analysis and turn in a screenshot of the 3 plots that I showed you. So those will look kind of like these 2 pictures up here. Then you're going to transfer those loads into the FEA study. You're going to run the FEA study and submit a stress plot that will look like this with the deformation exaggeration. If you have any questions, go ahead and come